everybody. So today we have the pleasure to have as a speaker Professor Gabriel Carlo from the Comisión de Energía Atómica from Argentina in Buenos Aires. And Gabriel studied at the University of Buenos Aires, and then he moved to the Institute of Complex Systems in Dresden, where he works with Schomerus. Did you work to the institute or to the university?
To the institute.
To the institute.
Yeah, to the Max Planck for the Physics of Complex Systems.
Yeah, the Institute of Complex Systems, yes. And then he also did some work in Como in Italy with Giulio Casati. And from then he's back in Argentina, and now he's going to talk to us on majorization-optimized quantum machine learning. Okay, Gabriel.
Thank you very much, Hilda. Thank you for inviting me. Thank you, Barbara, also for inviting me in the context of this beautiful school that I think that everybody is enjoying. And I would like to talk about a new tool I've been working with for the last, not even the last couple of years, I would say. It is something that takes into account too many ingredients. That is the quantum part, that in our case is referred essentially to quantum circuits in the context of quantum computation, and also machine learning. Machine learning in the usual sense that we are nowadays hearing in almost every aspect of life, that is the artificial intelligence sense, but at the very basic level. And we combine with this a new criterion we have introduced that is called majorization criterion, that is based on a measure that I will briefly describe in the first slides, that takes into account the spreading of a distribution in order to classify circuits in terms of their complexity. That is something highly non-trivial. For arbitrary quantum circuits, knowing if they are, for example, classically simulatable or not, it's not a very simple task. You have to go circuit by circuit and do specific demonstrations in order to know that. So, the summary of this talk is like this. First, I will talk you about what is called quantum reservoir computing. That is simply a classical machine learning model coupled with a quantum device. Then I will proceed to explain you what it is, this reservoir that I have said that is implemented in our case with quantum circuits. And these quantum circuits belong to the class of the noisy intermediate scale quantum ones, that are the ones that are being even commercially developed nowadays. And also, we are going to use the majorization principle to select in order to see which are the best suitable, not only quantum circuits, but also the best suited architectures in order to perform these tasks using this model. And then I will go to show you that, well, one of the main difficulties that we find when we try to use quantum computers, that is the noise. That's why we call them noisy intermediate scale. Not only intermediate scale is important in the sense that we have not that much qubits, though the scaling up of qubits have been very important in recent years, but the other important thing is that we have noise. And the noise up to now is completely unavoidable and not neglectable. So we have to take into account the effect of noise in this model. And surprisingly, some kind of noises are beneficial and not a problem in order to implement this model for calculating complicated things. And of course, this tells you where to put the effort at the time to implement mitigating strategies for the noise that are also a very important field related with quantum computation. So, the plan of the talk. First of all, I will go into preliminaries. I will do a small introduction of where are now in terms of quantum technologies, and also give you a sketch of what is expected for the near future. Then in the proper introduction, I will tell you, for those of you who don't know them, but I think that everybody nowadays knows what is a quantum circuit, but thinking that this is also school, I will give you an introduction of quantum circuits and also a brief one on the majorization criterion. And then I also will explain you what I'm talking about when I say that we use a model that is called quantum reservoir computing. Then I will go into the specifics of our model, and I will show you the performance of this model, comparing it with the majorization classification of the reservoirs. At the end, I will go into the effects of noise in this model by presenting you with the most usual quantum noise models and tell you which of them are beneficial and which of them are not. Of course, all this, even though it is towards application, it's always a proof of principle. I don't pretend to give you experimental results or something like that here. I only will show you a proof of principle that could be translated into experimental proposals, but also in non-trivial theoretical studies, because there are a lot of things that we don't know even from the theoretical point of view. And at last, I will give you my conclusion. So, in the preliminaries, I don't know if it can be seen. Well, one shocking notice back in 19, was the announcement by Google that its Sycamore processor that had 53 qubits was able to reach quantum supremacy. This, more or less, was tested with random circuits. That's why they are important nowadays, essentially, but for other reasons also, but this is the most prominent one. And this test was made with some measure, that is the cross entropy applied to see if the noise allows you to reach quantum supremacy. I put a question mark here because very soon after this, a lot of people criticized this alleged achievement, and they nowadays have proved, in principle, quantum supremacy with another device. But okay. But what happened? Soon after that, IBM, I think, felt touched by this and started rushing in their development of these quantum devices. And then the last year, they released the IBM Osprey. All of the processors have bird names. I don't know why. And what is really evident is that the qubit number growth exploded. I mean, they really made some progress in scaling up the processors. And yeah. Yeah. Everything is in discussion nowadays. I mean, yeah. No. So, they solve the sampling from random circuits. They use random circuits. I will go into more or less the details later, but just to give you a decent answer, they put random gates in their circuits, and they produce outputs. They sample from these outputs, and they try to reproduce that distributions with the classical calculation. And they have used their most powerful clusters, and they say that, for example, the most famous claim by Google was that it would take, with the most powerful computer, something like 10,000 years to reproduce something that they have made in a few hours. So this is the thing they did. And sorry. This is the basic architecture. These are qubits arranged in this sort of H scalable distribution, and this is a picture of the processors, and this is the scaling in the qubit capacity. Yeah. Sorry. Yeah.
My question is, when you tell me that there are 27 qubits or 65, et cetera, that means those qubits are substituting a one gate in a normal computer circuit?
No, essentially this play the role of the classical hardware. The gates, you apply them on the qubits. You perform unitary transformations of single qubits, 2 qubits, n qubits. Essentially, the set of logical gates of classical computation is mapped onto unitary gates, unitary transformations. Very simple ones for 1 qubit, more complicated ones if you think of more than 1 qubit. That's the idea. No, that I don't know. It depends also on the specific quantum algorithm, because each algorithm is a word in itself in quantum computation. So but this is the plan. This is not, obviously, this is not stopping here, and they make some daring assumptions or daring promises. At IBM, they plan to release this year the first quantum processor that overpassed the 1,000 mark, and they plan to interconnect them with classical and quantum communication and reach in the near term around 10 to 100K. There is an order of magnitude there, so perhaps that tells you that it's daring the promise. So this is the state of the art. This is what's going to happen in principle in the next few years. So I think that trying to exploit this huge movement around these things is a wise thing to do, and perhaps also funny. Here in Brazil, there is a supercomputer, a classical one, that simulates up to 35 qubits. This computer is based in the CNEA-CONICET Tech Center of Bahia, and we have been able to use it for our calculations, for some of them, with the people at the CBPF with whom I collaborate, that are Raúl Vallejos, Fernando de Melo, Alexandre Tacla, Nina Machado O'Neill. And this is a big achievement for Brazil, and they have baptized the computer. Its name is Quatomu, that I think it means quantum in some original language from the original people. So this is also important from the local point of view for Latin America. So what is a quantum circuit, for those who don't know what it is? We have distinguishable spins, qubits, in your resistor. This is your hardware. Here I put 8 with these labels. And then what you do is to apply these logical gates that are represented by these symbols here, but never mind, these are just unitaries, unitary matrices applied to 1 spin, to 2, to 1, and so on, in this model that I present here. What you do in a typical quantum computation is to prepare an input state that means a state of the qubits, then made this state evolve in this direction, that is the direction of the computation. Remember, we always read the evolution operator in this sense. In a quantum circuit, we read them in that sense. And then you perform a measurement on the register. On the computational basis, that is the 0-1 basis of the qubits. That, fortunately, you were explaining before me and make my life easier. So, some examples of the things. This is the Hadamard gate, that is essentially the smallest realization of the Fourier transform that takes you from one of the basis states into one superposition. Then this is the sigma x, that is the NOT gate. It negates, it goes, thank you again, it goes from 0 to 1, 1 to 0. And then you have a phase gate that is usually this one, and another phase gate that is called, for historical reasons, this is called the P/8 gate, because you can take a common factor of P/8 here because it's an irrelevant phase, but essentially it's a rotation around the axis of the spins. And this is an example of a 2-qubit gate that negates the second qubit in which it's acting, depending on the state on the first qubit. This is the analog, sorry? Well, these are pulses. These are pulses with microwaves that, depending on the time you apply them, you do a rotation, and then with rotations you construct them. But that depends on the architecture. That depends on the architecture. There are several providers like, for example, Google, Rigetti, IBM. They do it in different ways. No, I will go into that details a little bit later. So these are just examples of the most commonly used single and 2-qubit quantum gates. I have something wrong with this. Okay. So in our calculations, what we use is random circuits that are taken out from a family, a given family of quantum gates. We put them names in order to distinguish them and classify them. We call G1 this set that is made up of the control node that I showed you before, the Hadamard, and the NOT gate. And this is the example of the left. No? And this is what I was talking about previously, that the sampling from random circuits, from random quantum circuits, is strongly related to be a hard task for any classical computer. So it is used for the demonstration of quantum supremacy. And besides this family, we have considered the one that we call G2, that it's a family where we change the NOT for the phase gate. And this is the generator of the Clifford group that is known to be a non-universal and simulatable gate set. The G1 family is a subset of the G2. And then we have considered the G3, where we change this phase gate to the T phase gate. And this is universal. Universal in the sense that you can approximate any unitary, any quantum gate, at a desired precision by using this set. That perhaps is a better answer for what you were asking me. I mean, you made a finite approximation of any unitary with this set. It is proven, but of course to a given level of approximation. Sorry. Yes, you have the gates. Okay. So we consider several families of gates. This one is motivated by different reasons. It's called the match gate. But the main reason for us is because it's an alternative to a universal family in this sense. And it's, the motivation is because it's interesting from some mathematical abstract problems of perfect matching of graphs that involves trying to connect each vertex with just one link, and sometimes you can, sometimes you cannot, and these sort of things are solved with this sort of matrices. But in our setting, what it is important for us is that it's another universal family, but when you consider not qubits that are not neighbors. This is the way to construct it. You take the elements from the Hall measure and belonging to the unitary 2 group. And also we consider some diagonal gates where you take these random faces here. And we have considered gates that are diagonal applied to 2 qubits, to 3 qubits. This is the number of them that we can construct, and to all the qubits that is only 1, of course. Well, these are examples of quantum gates, and we have classified their complexity, or essentially their complexity, through this majorization principle that is being recently done by us, and we have also started to apply it with specific architectures, the ones that are represented by essentially all the main producers of quantum processors, and also considering noise. So, what is this principle? What is the criterion, essentially, that is based on the principle, the majorization criterion? Well, let's take 2 vectors, P and Q. Let's order their elements in non-increasing order. And if the partial sums that are called cumulants, all of the partial sums of, let's say, Q are greater or equal than P, we say that Q majorizes P, or P is majorized by Q equivalently. And one example is here, no? It's a clear example where this vector majorizes a general one, and this one is majorized by all of them. The idea is that this majorization measures the spreading of the distribution. It's somewhat a precursor of entropy. And what we have found is not the Lorentz curve itself, but the fluctuations of the Lorentz curve can discriminate between circuits that are universal and those which are not. But not only that, they also detect the complexity. That is a slightly different concept of some circuits that are non-universal, but they are difficult to simulate at the classical level. And we propose this criterion as an alternative to other complexity criterions, like for example, measuring the statistics, the level statistics of the reduced matrix, that is the entanglement spectrum. This is an example of the majorization curves, average over 500 realizations of random circuits. This is an example for the G1 family, and all of them evolved in a way that they reach the hard limit. In this case, the hard n limit. For example, we have taken 8 qubits, so this will be the hard 8 curve. So, increasing the number of gates, you get you go into the sense of the lower majorization. But as all of them coincide in the limit with the hard measure curve for the Lorentz curve, the thing that it's a sum. Some say, yeah, you have to sum. These are the partial sums of these vectors ordered in non-increasing order. So if you have this ordering here, of course, you sum all the normalized vectors at once, and this is the one that majorizes everything. And conversely, if you have the uniformly distributed vector, it is majorized for every other vector. So, but this is not able to distinguish between a circuit that is more complex or less complex, no? So we have found is that the fluctuations can distinguish the complexity, and we think that, for example, it's better to measure these things in order to classify the complexity of a quantum circuit, comparing, for example, with the entanglement spectrum, because even if you have to trace out, for example, the half of the register, you still need a matrix that gives you again the size of the vector that we have to evolve, and then you have the diagonalized matrix that goes as n to the 3. So it will be difficult to compare with this, that is just evolving vectors. It's very simple in that sense. And here, the takeaway from this criterion in this case, the only thing that is important to remember here is that the circuits that are non-universal, non-complex, are clearly distinguished. I mean, the fluctuations are clearly greater than those fluctuation curves that corresponds to universal or complex behavior that are essentially these circuits. We remember that these two families were universal, and these two families were non-universal but very complex to simulate classically. These are the Haar curves, and well, there are some symmetries. For example, the match gates preserve the parity symmetry, so if you start with a given state that has the parity, it keeps the parity, so the dimension of the Haar space, the dimension of your space is reduced, so the Haar measure in this case is smaller. But sorry, Haar is the measure. Haar n, the number of qubits. This is only because of symmetries in this sense. Yeah. 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 Okay. Well, yeah. No, but no, because the problem is that when you have different circuits, different families, you have to prove that they are simulatable classically or not. This is not a trivial task. And with this, you can do it statistically. That's the motivation, essentially, to simplify that. So then, let's pass to the toy I want to describe. Well, what is the quantum reservoir processing? Well, in principle, this is one of the first articles I have news of about talking about quantum reservoir processing. Essentially, it's a model that can perform not only qualitative tasks like recognizing if a quantum state is entangled or not, but also quantitative ones like estimating entropy, purity. I mean, it's quite versatile, and it could be used for many things. There are already reviews on the subject that essentially are based on the opportunities and experimental opportunities that one can find by exploiting this. And essentially what you exploit is the quantum nature of a given physical system, and this allows you to select a very simple training strategy that is classical, but it's a classical machine learning algorithm that benefits from the pre-processing of the data by means of this system that is the main feature of quantum reservoir computing. Specifically, it can be used, for example, to calculate the properties of excited states of molecules. That is a highly non-trivial problem, as many people here, many lecturers have said in this school. The many-body problem of a molecule it's sometimes intractable in terms of numerics. So essentially, this is explaining what the core of this application, but I will go into the details later. But keep in mind that it can be applied to predicting excited states from just knowing the ground state. So this is a scheme of what is the quantum reservoir computing. What you do is you start with an input state that encodes some information. It could be the input state itself, like in the previous slide that I said that, for example, it could be useful to predict the properties of excited states, knowing just the ground state of a molecule, but also you can enclose a time series, and you can predict time series. And it has been used in this context also. There are many entanglers that are the quantum substrates that you use to process your input state. For example, people use NMR, trapped ions, bosons in lattices, superconducting qubits, the quantum circuits that we're going to use, and photonic processors. Sometimes, quite often, people use, for example, the transfer field Ising model, where the coefficients are sampled from Gaussian distributions. So, after you apply the entangler, you perform a measurement. In our case, will be a measurement on our record, on our qubits. And this measurement provides you with the data that you feed into the classical machine learning unit. The measurement gives you some expectation values here that you put in your classical machine learning unit that, because of the pre-processing made here and condensed with this measurement, this machine learning part could be very simple, even a linear regression model, that is what we use. And then you have the prediction of the properties Y of these inputs X. Well, the idea is to select the quantum reservoirs from quantum circuits that are complex according to the majorization criterion. What we do here, in fact, is the opposite thing. We test all the circuits and verify that the majorization criterion is a good one to select these specific quantum substrates to perform these calculations. As I said, we are going to solve a chemistry problem that is finding properties of excited state of molecules, just knowing the ground state. Just to remember, if you want to represent an n-qubit state, you need a vector that is a size of 2 to the n, a classical vector of 2 to the n. But a NISC device that I told you before, for example, the one that is nowadays available, it's around 400 qubits, so it's of the order of 100 qubits. The classical analog of this is intractable. I mean, you have to think of a vector size that is, you cannot simply put it in a classical memory register. It's huge. So this is a good thing to do heavy calculations. And here I will take 2 examples just to illustrate the principle. The lithium hydride molecule, that is a very common molecule used in quantum chemistry, and water, for a given range of bond lengths between the atoms and a given angle for the water. We calculate the electronic Hamiltonian, and we calculate numerically and exactly the ground state and the energies, E1, that is the excited one, and the ground state energy. And they are calculated directly in the qubit space by making a Jordan-Megner transformation, so that to avoid any translation of the ground state. We already have it in the qubit basis thanks to this. And No, we calculate with in the qubit base, yeah, right. Then what we do is we train the model with a real vector that is composed of local Pauli measurements on these qubits. X, Y, and Z Pauli operators are measured on the register, and then these results are fed to the classical machine learning algorithm. This is the thing what we do is to evolve some random circuits of the order of 400, for example, for different values of this configuration of the molecules. And what we do is to predict this difference in energy, essentially the excitation energy. This is just an example. This is the target function. No? And this is done for what is technically called unseen configurations in the parlance of machine learning. The cost function that we minimize is the mean square error of this model. I mean, the W is called generically the matrix model, is in this case will be a vector, and you minimize the mean square error subjected to some regularization that prevents overfitting. If you have, this is linear regression. So if you have a lot of points and then you happen to have a point there, you want to, your algorithm will try to fit also that point, but you really want this curve, not this one. So by also asking the model to have a constrained L2 norm, we prevent overfitting. And then we train the model. We have used 300 different radii, and we just used 30% of this in order to test the results. The 70% is used for training. And we do extrapolation, non-interpolation, in order to make the results more rigorous. We have implemented this in commonly accessible libraries. Essentially, for the quantum computation part, we use Qiskit, and we use sklearn for the linear regression. You just call it with just 2 lines of code, and then it invokes the rich regression algorithm. And our code is available. If you're interested in playing with it, I can give you the reference, and you can go to GitHub and play a little bit. So this is a graphical representation of all this, just to be really clear. We have a molecule, for example. We calculate by diagonalization the ground state, and we initialize in this ground state the evolution by means of a quantum circuit that is, in principle, selected using the majorization principle. We test the efficacy of the principle in order to validate it in this work. But being validated, you can use it to verify your circuit or your hardware is good enough to perform this task. And then you measure, you obtain this real vector, feed it to the machine learning unit, and then you make the prediction. It's very, very simple. And these are the results. The solid lines stand for the lithium hydride here, and this is for the water. This is a harder task. It requires a little bit more of qubits, but the performance of the circuit we have verified behaves following the majorization classification that I was telling you about before. And what we see is that the families that were non-universal, G1, G2, perform bad, and the performance is bad even in the sense of growing number of gates, so it doesn't get any better. And we will try to explain qualitatively why. On the contrary, the G3 family, that is the universal one, is the overwhelming best performer of it. And the stabilization of this performance is around just 200 gates, even less. To have an acceptable value, we have to run just of the order. Sorry? No. No, I'm simulating it. we cannot access that. That will be the next step and will be very interesting to access it. No, for the moment it's noiseless. Then the noise comes. But it will be really, really rewarding trying to convince someone to, because, you know, if you want to do it with a small quantum computer, they allow you to use it for free. But if you want to go to a real one with hundreds of qubits, you have to pay. That's the problem. Yeah.
Why do you come to use machine learning after using quantum reservoir computing? I mean, isn't the reservoir computing is sophisticated or not machine learning?
Could be. You have a special case of this, that is the variational quantum circuit solvers, that you parameterize the quantum circuit. But the problem with that is that you have to rerun the quantum computer. You have to optimize all the time, and then that is very costly. With this, and just with a very simple machine learning part, very simple, you save all that. And nowadays it's costly to do that. That's why we try to use this hybrid. That not only us. I mean, this is something that is exploding nowadays. Several groups are trying to do it. Can I exceed a little bit up my time, or because I don't think I'm... Okay, thank you. I will rush. Then, well, the G3 family performs very well. It's the best one. Match gates that are universal also perform well, not that well as the G3 family. And the diagonal circuits that are, they have a defined number because of the reasons I told you before. Okay, perform well, but not so well as the universal family G3. And the problem comes when you try to use the most commonly used system or reservoir in this case, that is the Ising model. You have to trotterize it. You have to use the split operator method. And then you have to implement rotations. I mean, it's not very easy. It depends on the architecture, but sometimes you have to use a lot of gates. And this is very, very punishing in terms of gate cost. And it had to exceed our scale of number of gates in order to reach a mean square error that is a decent result. So, how can we explain this with a very, very simple model, a toy model made up of 2 qubits? In this case, we have relatively few multi-Pauli operators, and we can express the system in terms of these operators. But the Pauli space is still big. It is a 16-dimensional space where you want to see the structure of the state you evolve with it. The only way to see that I know nowadays this sort of complicated topologies in 16-dimensional space or in high-dimensional space is this technique that has been very successful in many areas, in biotechnology, for example, that it's called the uniform manifold approximation and projection. It essentially has 2 steps. They try to sense the topology of your data in this 16-dimensional space and then project it in a meaningful way in a space that you can see. It selects arbitrary axis and projects it into bidimensional space, for example, where you can see this. And we have designed in 4,000 random circuits to see what's happening with this toy model here. We evolved it for a long time, of course. And this is what we see. In the case of the G1 and G2 circuits, that is at these 2 plots, as the number of circuits, as the number of gates increase, they will concentrate on a dense region in the Pauli space, let's say, and this produces a bias on the results. And this concentration explains why the mean square error keeps on growing and never goes down. This is the uniform distribution that gives you an idea of what is in this representation the Pauli space. For the G3 family, we see that the covering is really a good approximation of the uniform covering. The match gates behave quite well, though they have some kind of a hole here. We don't know to which reason we can attribute this. Perhaps it's related with the symmetries. And the diagonal gates are more sparse in the covering, and perhaps this also has to do with the sparsity of these gates. So this is a form to qualitatively interpret with a toy model what's happening here. Because essentially what we measure when we measure the local Pauli operators after evolving through a quantum reservoir, what we are doing is measuring multi-Pauli projectors. That what they measure is the many correlations inside the input data. And that is what the machine learning unit can learn. I mean, these correlations. This is the important thing about the entangler that transforms in the Heisenberg picture. You can see that in reality what you are measuring is not a local operator, but all kinds of long-range correlations in the original input. That's the trick, to let the reservoir do your hard job. And in a sense, when you measure locally, what you do is to compress the data. Then you have what is technically called an enhanced space for your data, an enhanced feature space for your data. So, but the noise is unavoidable. That's a problem, as I said, when you deal with these new quantum processors. They cannot get rid of noise, of course. The noise is usually represented by the Krauss operator representation that is there. You have unitary transformations given by the gates, the unitary gates, but then you apply noise, a noise operator that it's no more a unitary operation. So we will describe this qubit system now by a density matrix because we have a non-unitary evolution here. We make an approximation that is to apply perfect gates without noise, but noise to the idle qubits, the ones that are not affected by the gate itself. So we use the usual models. Perhaps some people here is familiarized with them. This kind of noise that models energy loss. This is the amplitude damping. It's like a two-level atom that decays and by spontaneous emissions and emits a photon with a probability that is embodied in the letter P. Then we have the phase damping channel that is a loss, kind of loss of information without loss of energy. It's represented by these Krauss operators. And then the depolarizing channel that introduces what is called the Pauli error. That is these are the Pauli matrices, and they are applied with a probability that is equal to p-thirds. So we use this, and what we see is that we reproduce the same problem just with the G3 family of gates, and for low noise, with small noise, we have found that the amplitude damping, it's a better performer. I mean, a quantum circuit with this noise performs better for this quantum reservoir model than the depolarizing and the phase damping. And the performance of them is always worse than the noiseless case. And for a large number of gates, all the information starts to be lost because you are introducing classical probabilities and start to lose the coherence information that lies inside the initial state. How can we explain this? Well, essentially, if you think of a two-step process, where first you evolve with a unitary gate and then you apply noise, you can represent your state in terms of the multi-Pauli operators in this fashion. This is the action that the different quantum noise channels. This is another way of calling these different kind of noises in the quantum computation terminology. This is the action that the different noises make when acting on the Pauli matrices of a single qubit. And as this is considered to be like a direct product of noise, we can think what's happening when we have the action, a non-trivial action of the noise on a given qubit. So we can see something important. There is a difference, a qualitative difference between the depolarizing phase damping and amplitude damping. This is what is called a non-unital noise, in the sense that it doesn't preserve the identity. And this is very important. This is a critical difference that explains what's happening, why the amplitude damping is a beneficial noise for this sort of protocols, and the others should be prioritized in order to correct the calculations. If you use if you suffer from depolarizing or phase damping, what's happening essentially to your state is that the multi-Pauli coefficients get attenuated by this prefactor that depends on the particular noise. But if you use the amplitude damping, or if you suffer from amplitude damping, and you think it, for example, acting on the J qubit, as I was saying, when you have one of these, you have to consider two multi-Pauli operators of this shape, one that has the identity as is called K on this J qubit, and another one that has the Pauli seed matrix acting on the same qubit that it's called Py. Then the coefficient after the noise of this action of the noise, this particular thing, will become a linear combination of two previous coefficients, the coefficients that are produced by the unitary action. So even if AI is 0, not like in the previous cases, even if the original coefficient associated to this qubit is 0, you have a new component because of this. So the action of the amplitude damping is equivalent to adding extra components in the Pauli space. That is the space in which we measure, remember, our information, and the vector is produced with these measurements in order to fit the classical machine learning unit. So this is, again, the toy model that I have presented you with a very simple example with just 10 gates and P 0.2. And what we see is very, very clear cut. In the region of the 16 coefficients where you don't have an expression, I mean the coefficients are 0 for the noiseless case, but also for the depolarizing and phase damping cases, the amplitude damping has non-zero probabilities, also here. So this is the critical thing. And these non-zero values will give expectation values there, and introduces a better sampling of the initial state. It's equivalent to having more gates at the same price, not implementing them and having more gates. So we made a long simulation with this. We performed it with several gates with this toy model, and we see it again with this representation that the amplitude damping fills the Pauli space in a more efficient way compared to the noiseless case, and also to the depolarizing and phase damping case. So I arrived to the conclusions. We have proved that the majorization criterion is a valid criterion in order to select the circuits, but also the architectures that you have to use in order to make to have a good performance of this quantum machine learning model. This is a powerful tool, because otherwise you have to go through the calculations and do a lot of evaluations. With this, you have just to evolve a vector and see what's happening with the statistics of the fluctuations of the Lorentz curves. Then we also discovered that some kind of noises, the amplitude damping in this case, can be beneficial for the model, and still we we are restricted to small noise because otherwise you start to lose the information, the initial information. But anyway, this is a significant threshold. Nowadays, we are lower than this in, for example, in the computer, in the quantum processor of IBM, the Eagle one of last year. So this could be already implemented and tested in an experiment. And the depolarizing channel is the one that mostly attenuates the Pauli components, so this should be the priority in order to correct noise. And what we can do with this, I mean, in this context, in the people that is interested in quantum chaos and complex systems, well, there are a lot of things in order to profit out from this, a lot. I just mentioned 3 of them. We can, for example, try to predict the fluctuations of the Lorentz curve at the level of random matrix models. That is a thing that a lot of people here know what it is about, and it's something that is an open problem. It's a very hard problem, but it's a daring problem, I think, and a very interesting one. Then we can think of predicting excited states, very excited states of quantum chaotic systems, and try to find their morphology, try to classify their morphology. This is always difficult. I mean, numerical calculations of classically chaotic systems at the quantum level is really demanding. So this can be used to train one of these machine learning models in order to predict these excited states. And then something that is also interesting nowadays is try to classify directly, if you already have your states calculated with this training, to retrain your system to measure localization on those states. And for example, nowadays, for partially open and open systems, this is a long-standing open question in quantum chaos. There is more, equal, or less localization, and on what objects. Nowadays, the debate is growing, showing that there are some strange objects in which the localization is present, like segments of trajectories, not on trajectories. That's quite astonishing, and it would be very nice to test for different systems what's happening with this tool. So this has been published here, and fortunately we have some media repercussion in Spain and has been published in the newspaper. So thank you very much for hearing me all this long time.
Interesting talk. I mean, any questions? Okay, there first. Let's start.
Hi, can you tell a little bit more about the application that you mentioned, the localization measures? What exactly localization measure are you thinking?
Well, there are a lot of localization measures. For example, inverse participation ratio is one of them. It's basis dependent. It's not the best one. You can think of many more. But the idea is to avoid calculating the, for example, well, if you go to quantum phase space, this problem of dependence on the basis is partly removed. I mean, if you find localization in phase space, you are pretty sure that your state is localized. But calculating a distribution in phase space is quite demanding. Calculating the Wigner function is demanding, the QCMI is demanding. You can avoid completely that if you train a model to learn the quantum structure of phase space. And then you have just to feed with a state vector, and this machine will tell you if this is localized or not, and many more things, of course.
Thank you.
Yeah, I don't know if it is a question or a comment, but let's say a sort of intermediate.
Go ahead, don't worry.
I mean, going to the specific application that you considered, I understood that you, let's say, compute classically the ground state, then that is your starting point to, let's say, understand something about the excited states.
Exactly, yeah.
Now, an immediate, let's say, objection that one could raise is that if you have the classical capability to compute the ground state,
sure.
Why you shouldn't?
Sure.
Okay.
But that's valid for
No. But I'm going there.
Okay.
So I think a more promising, let's say, application that you could think would be to construct the ground state using a variational quantum circuit, and then use that information to reproduce the excited states.
Yeah.
But then probably it would be interesting to compare the, let's say, the performance of this algorithm contrasted with using the variational quantum circuits to directly address the excited state. That is also possible if you change the cost function.
Yes.
So do you have in mind something along that direction?
We have in mind
Okay.
something like that. Yes.
Okay.
Yeah.
Okay.
That's very, very good comment. Thank you very much.
Yeah.
Thank you for the talk. Can you go to, back to the slide where was the draw of the protocol?
The draw, sorry?
Yeah, the draw of the circuit.
Of the circuit.
Yeah.
Let's go. Let's see.
Back. Yeah.
This one?
Yeah, that one.
Okay.
So you have a lot of families, right? Of gates.
Yes.
And you take your initial state that you initialize according to the diagonalization, the exact diagonalization that you use.
Yes.
And you put your family. So I want to understand where is the majorization part goes in, like.
No, I said that it was a proof of principle. We have tested that the circuits that corresponds to the more complex one, according to our criterion, are the best performers in our model.
And the most.
So it's a test, it's a benchmarking test that this criterion that is quite easy to implement could be a good way to select what to use in order to apply it.
Because I am thinking in geometrical terms.
Yeah.
Don't enter into big
No. I'm thinking in geometrical terms, and you have your space of all quantum channels,
Yes.
quantum, and the hard measure will be the center of the space of all quantum channels.
Yeah.
And the majorization is more stronger at the center of all quantum channels because it's a hard measure, so you majorize in the center. So according to that, there are some certain families of circuits that are very, very far away of that center.
Yeah.
And it's some kind of clear that they will not give well results using the majorization method.
But
the question is why use it in that.
But there is no, because for future hardware, for future implementation, for future experience, you need to test if what you are doing is correct or not. It's not that obvious.
Okay.
It's not that obvious. There is a gray zone where you have to do your homework and prove that this circuit or this protocol is universal or not. It's not that easy. It's not trivial.
Questions? Yeah. Can you collect it because I cannot walk?
Well, thanks for the talk. I have a question not strictly to the quantum part, but on the end part of this diagram. How do you, well, first, your benchmark was on the time you took.
This part?
The benchmarks you made on the majorization. It was on the time it took to do calculations or on the how precise the results were?
No, how precise the results were.
Yeah.
I mean,
and how do you train the machine learning?
The machine learning is trained by several runs of random circuits that give you measurements. You obtain a 3n vector, and then you fit a rich regression method with regularization and obtain a matrix model. And then you go to unseen results, I mean, results that you have, but you haven't used to train the model, and verify if this cost function is reasonable.
Yeah, so you have like a data set for?
Sorry?
You have a data set with this?
Yes,
data?
we have a data set. We have something like 300 ready for the different molecules we have used.
Okay.
Yes. Yes, sure.
Okay, thanks. I have a couple of very short questions.
Yeah, sure.
One is about the effect of the noise that you say that it can help. Is that something, let's say, similar to stochastic resonance?
Could be, could be.
Do you think it could be?
Yes, yes, because you can model, as you know, with the amplitude damping, one of the generalizations is the friction, ohmic friction. So perhaps it has to do with that. And there is a puzzling question, it is that this sort of noise is like expanding in the Pauli space, but it's contracting in the phase space.
Okay, thank you. I have a short question that
Yeah, sure.
some people may be worried about, and is for this, when you do quantum computing and things like that, most of these qubits or whatever you use, they only work at very low temperatures.
Yeah.
So, I mean, meaning how much do you expect these things to spread when you look at that particular problem? I mean, the fact that IBM or Google or so can do it.
Well, you have to believe them. I mean, it's a difficult task, but they have developed a lot of error mitigating techniques and correction that they do afterwards with classical electronics. That is quite promising. I think that they are going to deliver, perhaps not that fast and not that astonishing that they promise around 100,000 qubits in the very short term. I don't think so. But nowadays, I changed my mind. Once I thought that this was plainly impossible, now I'm more confident on that.
I want to address the structure of the circuit because if I understand it correctly, your protocol depends on the circuits generating random states, right? Because the machine learning part is on the classical. Yeah. So you won't need like a reservoir computing to generate the states. You could like use a parameterized quantum circuit to generate random states and then make the protocol of machine learning after this. So you're not sampling random circuits, you're sampling...
No, I'm not sampling. Yes, I'm sampling
I'm saying
to generate data sets.
Yeah, but you could like, instead of sampling random circuits, you could sample like parameters.
Yeah.
So it could be the same as, you could use the same method with parameterized quantum circuits.
I would do the same method, but will be a different kind of model. No? But actually, I will try to use it. That is a very good thing to do, actually, to try to implement it in this sort of variational quantum circuits.
Okay, thank you.
Yeah.
I guess that's it. Thank you very much for...
Thank you, and thank you all.